Okay, so in this function we're going to talk about exponential and log functions, and you can freeze the video and read that first paragraph if you like. But I'm going to start with the definition of the natural log function. The natural log function is actually defined by the integral. So natural log of x is defined as the integral from 1 to x 1 over t dt, where x is greater than 0. Now the domain of the natural log of x function is positive real numbers, and the range is actually all real numbers. So if you wanted a representation for, say, the natural log of some number, let's say the natural log of 4, well, that would be, by definition, that would be the integral from 1 to 4 1 over t dt. So if you were to graph the function here, so let's say this function here is 1 over t, then if you integrate this function from, say, t equal 1 to t equal 4, that would give you this area under the curve, and that area would actually equal the natural log of 4. Now if you wanted to know the natural log of a number between 0 and 1, like natural log of a half, you might remember that natural log of a number between 0 and 1 is a negative value. Well, that makes sense here, because what you would actually be doing is, by the definition, you would integrate from 1 to a half, which means you're integrating from right to left. So it would give you the area under this curve, but it would give you the negative of that area. So that's how you would get the negative. Now, where do we get the number e? Well, e is actually the number whose natural log is 1, because since this function is continuous and 1 to 1, and the range is all real numbers, then there must be a value that you can plug in that'll give you 1. And so it turns out that for the natural log function, that value is this number e, which is an irrational number. Now I gave you e to a bunch of decimal places, but the exact value of e is simply e. And by definition, the natural log of e would be the integral from 1 to e of 1 over t dt, and that would equal 1. And so you could integrate from t equal 1 to t equal e, and then that area under the curve there would actually equal 1. Okay, now, since from the fundamental theorem of calculus we know that when we take the derivative of an integral, we really just get the function that's in the integral. So if I wanted the derivative of natural log of x, well, let's start with the definition of natural log of x, which is natural log of x equals the integral from 1 to x 1 over t dt. And then if you took the derivative of the left side, you just have the derivative of natural log of x. But if you take the derivative of the right side, the derivative of 1 over t dt from 1 to x by the second fundamental theorem of calculus would just give you 1 over x. And then if you go along to the chain rule, and you want to take the derivative of the natural log of u, where u is a function of x, then that derivative would be 1 over u times u prime. Now I realize this chapter is integrals, but I do need to tell you a little bit about the derivative of these functions. Okay, so number 1 here, finding the derivative of this is straightforward. Apply the power rule to x cubed, you get 3x squared. Apply the log rule to natural log of x, and its derivative is 1 over x. Here I'm going to apply this rule up here that I gave you. So here I have the natural log of u, and so the derivative of that would be 1 over u. So I have 1 over u, and then times u prime, which is the derivative of 2x cubed minus 5x plus 1. And then you can write that as a rational expression. And then this next one here, the derivative of this, you take the derivative of sine x, which is cosine x, and then you'd take the derivative for natural log of x, which simply be 4 times 1 over x, or 4 over x. And then this one, the derivative of natural log of tangent x, again, you would do 1 over u, since in this case u would be tangent of x. You'd have 1 over tangent of x times the derivative of tangent of x, which is secant squared x. So that would be secant squared x over tangent x. Now you could probably simplify that using some trig, but I'm just going to leave it like it is. A couple things that you might recognize here is that the derivative of natural log of x is just 1 over x, where x has to be positive real numbers. So therefore, the derivative must always be positive. So that means that this function is an increasing function. And if you found the second derivative by taking the derivative 1 over x, you would actually get minus 1 over x squared, and that function would always be negative. So since the second derivative is always negative, then the graph is concave down. Now if you graphed natural log of x, you would actually get something that looks kind of like this, and it would be increasing and concave down throughout the entire graph. Some properties of natural log of x, and if you know your log properties from algebra, then you know these are true. Natural log of b times x is natural log of b plus natural log of x. Natural log of b divided by x is natural log of b minus natural log of x. Natural log of 1 over x is the same as minus the natural log of x. The natural log of x to a power r is r times the natural log of x. And I'll just let you freeze the video and look at these three examples here that illustrate those properties, and then you can start back when you're finished looking at them. Okay, now let's talk about integration involving log. Since the derivative of natural log of u is u prime over u, then if we were to integrate 1 over u du, we must get the natural log function back. But actually, when we do this, we actually have to write it as the integral of 1 over u du is equal to the natural log of the absolute value of u, to avoid any negative values in the argument of the log. Okay, so let's say you want to integrate these problems down here. Now what I want you to notice down here is that the denominator here is not raised to a power. If it was raised to a power, we would probably use the power rule, but in this case, since u is just x cubed minus 2 to the first power, then we can let u equal x cubed minus 2, and then notice that du would actually be the numerator. So du would be 3x squared dx. So now we know that this portion right here is simply du, and that this portion down here is u. So that takes the form of du over u, and so to integrate du over u, we would get natural log of the absolute value of u plus a constant, and then we can replace our substitution for u by putting x cubed minus 2 in for the u value. Okay, now sometimes we might have to manipulate 1. So here's 1, and again notice that the denominator here is to the first power, so I have u equals x squared minus 2x plus 1. Okay, now du would be 2x minus 2 dx, but so notice here I have x minus 1 dx. Okay, well that's not the same as what I have here, but if you take this right here and factor a 2 out, then you'll get 2 times x minus 1 dx. Okay, so what I can do is I can take this integral and I can multiply on the inside of the integral by 2. That way the 2 times x minus 1 dx becomes the du, and then I can apply the formula for the du over u. Now remember though, when I put a 2 on the inside, I have to put a 1/2 on the outside. So actually this is going to be 1/2 times the integral, and remember the numerator portion that is du and the denominator is u, so I have 1/2 times du over u, and then when you integrate that using the formula, you get 1/2 times the natural log of the absolute value of u plus a constant, and then just replace u with our substitution that we used up here. Okay, so you get 1/2 times the natural log of the absolute value of x squared minus 2x plus 1 plus c. Now there are times when you can remove the absolute value, but that's only if you know that the expression can never be negative. Okay, Now on this one I have x over x squared minus 5 dx, and here I'm actually doing a definite integral. So let's go ahead and evaluate the integral first. So I'm going to let u be the x squared minus 5, then du would be 2x dx. So what I'd do is I'd need to multiply the inside by 2 so that the numerator would be the 2x dx, that would be the du, and then the x squared minus 5 is the u. So, but putting a 2 on the inside means I have to put a 1/2 on the outside. So I actually have 1/2 the integral du over u. Now you might be asking, where did the -5 and the -4 come from here? Okay, well, since I switched variables, I went from x to u, then I have to change my limits as well. So what I have to do is I have to ask myself, okay, if x is 0, what would the corresponding u be? So since u equals x squared minus 5, you plug 0 in here, and 0 squared minus 5 is -5. So when x is 0, the u is -5. And then you do the same thing for when x is 1. When x is 1, what's the corresponding u? So you would get 1 squared minus 5, which is -4. And so then when I evaluate this, I get 1/2 times the natural log of the absolute value from -5 to -4. Now you might remember that you don't need to convert this back to a function of x if you change the limits accordingly like I did here. So now evaluating this, I'll keep the 1/2 on the outside of the expression, and I'll evaluate this at -4. So I get natural log of the absolute value -4, then minus evaluated at -5. So I get minus natural log of the absolute value -5. And since those absolute values are positive, I'll just get 1/2 times the natural log of 4 minus the natural log of 5. And if you wanted to, you could use your log properties to write that natural log of 4 minus natural log of 5 is natural log of 4/5. Okay, so here's another problem. Here I can just let u I'll let u just be this entire expression, and then when I take the derivative of that, actually I'm going to let u be this entire expression, and then the derivative of that would be 2 cosine theta d theta. So here's the problem I started with. I had a 4 up here. So what I'm going to do is factor out one of the 2's out of the 4. So I'm just going to factor a 2 outside, and now this part along with the d theta is actually du. And so what I get the integral of du over u, and to get the corresponding u limits, I need to put minus pi over 2 into this expression. So 3 plus 2 times sine of minus pi over 2 is actually 1. And then I put pi over 2 in, so I get 3 plus 2 times sine of pi over 2, and that's going to give me 5. So then when you integrate this, you're evaluating it from u equal 1 to u equal 5. And then you get 2 times the natural log of the absolute value of u from 1 to 5, and then you just apply the fundamental theorem of calculus, and you get 2 times the natural log of 5 minus the natural log of 1, and then since the natural log of 1 is 0, then you just get 2 times the natural log of 5. Okay, I'll just show you one of these, and you can pause the video and look at the other one. Since tangent x can be written as sine x over cosine x, you can let u equal cosine x, and then du would be minus sine x dx. So since I need a minus sine x dx, I'll multiply on the inside by -1, and I can do that as long as I multiply the outside by -1. So then that would become minus the integral du over u, which is minus the natural log of the absolute value of u plus a constant, and then replace u with the cosine x, since that's what it equals. So now we have a formula for the integral of tangent x, and it's equal to minus the natural log of the absolute value of cosine x plus c. And also, if you wanted to, you could actually use the power rule to write this as natural log of cosine x, the reciprocal of cosine x, which would be natural log of absolute value of secant x plus a constant. And then likewise, if you go through this one, you'll see that you have a formula for integrating cotangent of x that you gained by using this log form of integration. So in the next step, I'm going to do some exponential functions, or the next video rather.